So in this video we're going to look at Taylor polynomials. So a Taylor polynomial, let's say p sub k of x for the power function or power series, for f of x centered at x equals c, is a polynomial of degree k such that the value at c is equal to the function's value at c. The first derivative evaluated at c is equal to the first derivative of the function evaluated at c. The second derivative evaluated at c is equal to the function's second derivative evaluated at c, all the way down to the kth derivative evaluated at c of p equal to the kth derivative evaluated at c of f. So if you watch the video for Maclaurin series, the only difference between Maclaurin series and Maclaurin polynomials and Taylor series and Taylor polynomials is the Maclaurin series, let me put this down here, is just the special case where c equals 0, where the center's at 0. And I've seen on the AP test before a question about a Taylor polynomial centered at 0, and that's really a Maclaurin polynomial. There's no difference. Now, as with Maclaurin series, so how do we find the coefficients? Because I know that this power series is going to equal a0 plus a1 times the x term, but since I'm centered at 0, I'm going to make that x, or sorry, centered at c, make that x minus c, plus a2 x minus c squared, all the way up to a sub k x minus c to the k. And so, just like with Maclaurin series, the nth coefficient will be equal to the nth derivative, evaluated not at 0 but at c this time, divided by n factorial, because, so I'm going to put a little because, just for those that didn't watch the Maclaurin series, so because the derivative with respect to x of x is 1, the second derivative with respect to x squared of x squared is 2, the third derivative with respect to x cubed of x to the third is 6, and in general, the nth derivative with respect to x to the n of x to the n is n factorial. So to rectify this multiplying repeatedly by exponents, I divide by n factorial. So that's going to be my coefficient. If you have that memorized, you can get the coefficients. Or you can also notice that the terms are going to be the nth derivative of f evaluated at c divided by n factorial times not just x to the n, but x minus c to the n. So either one that you memorize, you can construct these series for many, many examples. So let's look at a couple of those examples. Some easier, some a little bit trickier. Here's our first example. Find the Taylor polynomial of degree 3 for f of x equal x to the fourth minus x cubed plus x squared minus x plus 1, centered at x equals 1. So what I need is f of x, which is just this. I need f prime of x, which is just 4x cubed minus 3x squared plus 2x minus 1. I need the second derivative of f, which is 12x squared minus 6x plus 2. And since I have a degree 3 Taylor polynomial, I need the third derivative which is going to be 24x minus 6. Now, from those, I evaluate these at x equals 1. So I need f of 1, f prime of 1, f double prime of 1, and the third derivative of f evaluated at 1. When I put 1 in here, I get 1 minus 1 plus 1 minus 1 plus 1, so that's equal to 1. When I put 1 in here, I get 4 minus 3 plus 2 minus 1, which is 6 minus 4, 2. When I put 1 in here, I get 12 minus 6 is 6, plus 2 is 8. Now I put 1 in here, I get 24 minus 6, which is 18. And then using our rule, so I'm going to divide these by the factorials, a0, a1, a2, a3. So this will be 1 divided by 0 factorial. This will be 2 divided by 1 factorial. This will be 8 divided by 2 factorial, because it's for the squared of the second derivative term. And it's 18 divided by 3 factorial. 0 factorial is 1, so 1 divided by 1 is 1. 2 factorial is 1, so 2 divided by 1 is 2. Sorry, 1 factorial is 1, so 2 divided by 1. Okay, 2 factorial is 2, so 8 divided by 2 is 4. And 3 factorial is 6, so 18 divided by 6 equals 3. And this gives us our polynomial, which is going to be p sub 3 of x is equal to 1 plus 2 times x minus 1, x minus the center, plus 4 times x minus the center squared, plus 3 times x minus the center cubed. So that is our third degree Taylor polynomial. And as with Maclaurin polynomials and Maclaurin series, this can be used to estimate that. Now it's a silly problem because I have a polynomial, but this can be used to estimate that. So let's take a look graphically at what's going on. So what I have here is the function, and let's get this going. That is with the first term, so that has in it 1 plus 2 times x minus 1, so it's the linear approximation. I'm going to add the 4x minus 1 squared term next, so if I add this in, now it's a quadratic, and you can see we had that in there, and finally I will add in the 3x minus 1 cubed term. And that gives us a cubic. And you can see all the way over here, it looks like a really, really great approximation, but then since it's a cubic as opposed to a quartic, it moves away over here. So this is, the red is our Taylor polynomial, the blue is our original function. Now, one thing that's worth noting, because you might be wondering, well, hold on. This was a 4th degree polynomial to begin with. What if I got the 4th degree Taylor polynomial? Well, what happens is you actually get the same exact function. It's going to look a little different because I'm going to have x minus 1 and x minus 1 squared. But if you expanded and simplified, you get the same exact way to view it. And as I add on extra terms, I'm not actually going to add anything else because all of the higher derivatives will be 0, so it doesn't change anything. You can see as I add on more and more and more terms, I still have the same function. I don't want that. Okay, so that is that. Let's go on to a more annoying example, and I'll shorten this notation, but I'll use the same color scheme. Find the Taylor polynomial of degree 3 for g of x equals sine of x, centered at x equals pi over 3, and then use this polynomial to estimate the sine of, and this should be, I shouldn't have the, let me do it this way. I shouldn't have this. I should just have one parentheses. Okay? So, I'll do the same thing to start with. I need g of x, g prime of x, the second derivative and the third derivative. G of x is sine, g prime is cosine, g double prime is negative sine, and the third derivative is negative cosine. Okay, now I evaluate each of these at x equals pi over 3. So the sine of pi over 3 is root 3 over 2. The cosine of pi over 3 is 1/2. The negative sign is negative root 3 over 2. The negative cosine is negative 1/2. And then I need to divide through to get a0, a1, a2, and a3. I'm giving myself a little bit more room to write all these factorials. So I'll have root 3 over 2 divided by 0 factorial. 0 factorial is 1, so I get root 3 over 2. I'll have 1/2 divided by 1 factorial. 1 factorial is 1, so I get 1/2. I'll have negative root 3 over 2 over 2 factorial. 2 factorial is 2. Negative root 3 over 2 divided by 2 is negative root 3 over 4. And I'll have negative 1/2 divided by 3 factorial. 3 factorial is 6. Negative 1/2 divided by 6 is negative 1/12. So that gives me that the third degree Taylor polynomial will equal root 3 over 2 plus 1/2 x minus pi over 3 minus root 3 over 4 x minus pi over 3 squared minus 1/12 x minus pi over 3 cubed. And to evaluate this, so let me put this down, the sine of pi over 3 plus 0.1 will be approximately p sub 3 of pi over 3 plus 0.1, which is going to be, I have the root 3 over 2 plus 1/2. When I put pi over 3 plus 0.1 in here, I get pi over 3 plus 0.1 minus pi over 3, so I just get 0.1 when they cancel out. I have a minus root 3 over 4 times 0.1 squared, and I have minus 1/12 times 0.1 cubed. Alright, hopefully I have enough room. So this is approximately, I have root 3 over 2 plus 1/2 times 1/10 is 1/20 minus root 3 over 1/10 squared is 100th, so that will be 400 minus 1/10 to the third is 1,000th, so I'll get 1 over 12,000. And adding these together, so I can combine the root 3's by multiplying this by 200. So I have 199 root 3 over 400 plus, and I'll multiply this by, let me make sure I'm doing this correctly, 600. So I'll have 599 over 12,000. Okay, that was a little bit of a mess. I hope that made some sense to you. Let me sort of box in. This is my final answer for the approximation, and this right here is my Taylor polynomial. So a little bit of a mess there, but you know, same steps. And let's see one that's a little bit more abstract, but well, actually before, let me show what this looks like. So in here, let me change this to sine of x. Okay, and let me change that center to pi over 3. And this is kind of fun to see. So I want to go up to the third degree. So that's first, second, third. You're like, okay, that's a cubic function, and it looks pretty good over here. Okay, if I go a little bit further over there, it's fine. But watch what happens if I go closer and closer to the series, adding on more and more of these terms. It starts getting better and better. So I have this sort of, at this point here, I have a degree 20 polynomial that looks really great all the way out to, let's say, negative 2 pi. And then it starts to fall apart. But as I add more and more terms, it becomes closer and closer. We're still pretty far away if I just stop at the third degree, but that's what happens. Okay, last example. And that's one of these where we're given some type of function and a rule. I want to find the Taylor polynomial of degree 4 and estimate r of 0. So in here, I need to have r of negative 2. Yeah, I'll do it this way. I had the first derivative of negative 2, the second derivative of negative 2, the third derivative evaluated at negative 2, and the fourth derivative evaluated at negative 2. I'm told that r of negative 2 is 1. R prime of negative 2 is just the first derivative. So I use this formula and put in 1. So that's 1 factorial divided by 1 plus 1, which is 1/2. The second derivative is 2 factorial divided by 2 plus 1, so 2 over 3. The third derivative is 3 factorial divided by 3 plus 1, which is 6 over 4, or 3/2. And then the fourth derivative is 4 factorial divided by 4 plus 1. 4 factorial is 24 over 5. Okay. Now I can jump straight to my terms. So A0, A1, A2, A3, and A4. Divide this by 0 factorial, I get 1. Divide this by 1 factorial, I get 1/2. Divide this by 2 factorial, 2 factorial being 2, I get 2/6, which reduces to 1/3. Divide this by 3 factorial, 3 factorial is 6, and I get 3/12, which is 1/4. Divide this by 4 factorial, 4 factorial is 24, so I get 24 over 120, which is 1/5. And you could have seen I had an n factorial up there, that's why this is happening. So my fourth degree Taylor polynomial is equal to 1 plus 1/2 x plus 2, because it's minus and negative 2, plus 1/3 x plus 2 squared plus 1/4 x plus 2 to the 4th plus, I'll put it down here, 1/5 x plus 2 to, did I miss something? Yeah, I did. Sorry. I got rid of a bunch of this stuff. So this was the 1/2 plus 1/3 x plus 2 to the 3rd plus 1/4 x plus 2 to the 4th plus 1/5 x plus 2 to the 5th. Okay, so there's our Taylor polynomial. And I know that r of 0 will be approximately, as long as it converges here, it doesn't, but if it did, it will approximately equal the fourth P4 of 0, which will be, so I put in 0 for all this, I'll have 1 plus 1/2 times 2 plus 1. Hold on, I was an idiot again. So this should be 1/3 x squared, 1/4 x cubed, and 1/5 x to the 4th. I don't have this term. It's just the 4th degree. Okay, sorry. So I have 1/3 times 2 squared plus 1/4 times 2 cubed finally plus 1/5 times 2 to the 4th. And that will be 1 plus 1 plus 4/3 plus 8/4, which is 2, plus 16/5. So that's going to be, let's see, 1 plus 1 plus 2 is 4. I need to get this in terms of 15ths. So 4 is 60/15. So 60 over 15 plus 4/3, multiply top and bottom by 5, 20/15. Multiply top and bottom here by 3, 48/15. And my final answer is going to be 128 over 15. And I apologize for the mess I made over here. I hope this helped out. Feel free to comment below if you have any questions.